No, 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 no. Espera. Vale. Entonces. Yeah. Oh.
Okay, we are going to start the afternoon session with the course by Frederick Van Villan, which is a three-way out of equilibrium in many-body systems. So, Frederick.
Thank you very much, Gabriel, Alejandro, Jose Daniel. It's a real pleasure to be here. Not the first time, but each time I come back, this is even more pleasure. So uh, I was given a very difficult assignment. I was asked to talk about non-equilibrium physics, many-body physics, and technical stuff. The whole thing has to be done in 4.5 hours. So the first thing I will do in pictures, so that you just get out of your lunch in a smooth way. I will show you a couple of slides. Of course, it doesn't work. Oh, it works. Oh, there it is. So these are slides that I stole from Gavin Crooks from an old presentation of his, maybe 10 or 12 years ago. And he was giving a series of lectures on what it is to be out of equilibrium. So I figured if I have to tell you about non-equilibrium physics, I would start by telling you what I believe is equilibrium and what is not equilibrium. And from this movie, you see that there is obviously something very wrong, that there is something that is puzzling, that is telling us that things are not right because we have some sort of uh, in we have some understanding of the area of time. We know how things flow in our macroscopic world, and this is not going well along the flow of things as we know that. Of course, when this happens, this is much more interesting than when this happens. So this is just a glass of water. And for this, this is a movie, actually. Maybe you don't see it, but that's a movie. Uh, there is not really much happening. So of course, this is a caricature, but this is just to tell you that whenever there will be an arrow of time, a signature of the arrow of time, I will be speaking of out of equilibrium physics. And whenever there is no arrow of time, I can play the movie forward or backward. I will not see any difference. Then this is equilibrium. Okay? So that's my starting point. It's you can turn that into formulas, but it's a good idea to have in mind. You know, movies played backward or forward, no difference. That's equilibrium physics. So equilibrium physics, of course, we know how things go because we know that we don't need to know the dynamics to predict what's happening at very, very large times. Regardless of the dynamics, we know that if we wait long enough, whatever time that is, we will eventually sample the Boltzmann distribution. And the Boltzmann distribution tells us that the probability of observing the system in a given state is exponential in minus the energy of the system at that in that state, divided by a number that is a characteristic number of the environment that the system is bathing in. That's the temperature. So this we know. From the moment I drop the hypothesis that I'm working in equilibrium, I have no clue what the stationary state is. So the whole series of lectures will be trying to explore three different directions in which we can nevertheless say things rather universal about what's happening in the late stages of the dynamics in the steady or stationary state, non-equilibrium but steady, in systems that do harbor an arrow of time. Okay. So yes. The last slide, and you will be shocked sometimes at the way that I'm doing things. And this is something that is very peculiar to statistical mechanics. We do physics by dropping most of the physics, actually. This is the modeling step that is so entangled with the approach of statistical mechanics. We throw all the irrelevant physics, and the irrelevant physics may well be relevant to some other physicists, but to the statistical physicists, we try and throw away whatever is not useful for our understanding of usually emergent collective properties. So the idea is when you do statistical mechanics is to throw the water of the bath while keeping the baby, okay? So I'll be talking about fluids, but soon you'll see that my fluid is just a bunch of zeros and ones on a line, okay, on a lattice. So that's exactly what I'm talking about when I'm telling you about, you know, throwing the water of the bath and keeping the baby. I will try and make this as simple as possible, still retaining enough interesting physics so that we can work on it. Okay, I was told that I have to move left, which is fine with me, of course. Good. So okay. So maybe before I dive into the first chapter, I want to tell you what the three chapters or the three lectures are going to be about. First one is very simple. You take a pan, put some oil in it, maybe sprinkle a little bit of salt in there, heat it from below. Then you've got a heat current going across the pan, and you ask, okay, what can I tell about the structure of the microscopic states in that system when there is an energy drive, thermal drive, it could be, you know, particle drive, charge drive, whatever. But that's probably you've seen that Rayleigh-Benard experiment, maybe not, I don't know. But what I'll be interested in is describing the statistical properties of a fluid that is subjected to a drive. Okay, first lecture, that's for today. The one, there are two tomorrow. So the one that comes next is about systems that fail to actually equilibrate. You can wait as long as you like. They will never reach equilibrium. They are on their way to equilibrium, but they just don't get there for many reasons. So they are usually called glasses. And actually this, you don't even know if it is something flowing or something that is completely frozen in like a solid. So the second lecture, the one that I'll begin with tomorrow, is about glasses and theoretical approaches, many-body approaches to glasses, etc. The final one, and Laetitia has touched upon that already, with the same big names, has to do with active matter. So perhaps all of you know of this Perrin experiment, in which there's a sedimentation of colloids, colloidal particles. That's equilibrium physics. You know, you can predict what's happening to the profile of the density using the Boltzmann law. Fine. What's happening if you replace the colloids with bacteria? What's happening if you replace the colloids with active colloids, Janus particles that are activated by sucking energy from their environment and using that to produce motion, thereby dissipating energy that is not returned to the environment, unlike what's happening in this detailed exchange of dissipation and injection. So that will be the last of the lectures will have to do with active matter, and I will, begin with by telling you about a few models, and then I'll try and tell you that there is some interesting collective physics there as well. So I guess I'm all set. I have wrapped up in 8 minutes the outline of the 4.5 hours. Let me begin with the first chapter, okay? It's not super convenient, but maybe here. And here I have to share. Okay. So I am not as prepared as Laetitia is or was. I don't have pre-written slides, so I will write as we go along. I hope that will be understandable. So the first thing that I want to tell you about has to do with the first way of being out of equilibrium, which is when the system is driven by the boundaries. You know, when you think of this pen that is being heated from below and in contact with the air of the room from above, there is a warm thermostat at the bottom that is heating the system, and there is a cold thermostat, that's the air of the room, that is actually cooling the system, and there is energy that is going from the warm to the cold, right? So I'd like to design a statistical mechanical model in which I can do things, right? In which I can actually move on and, make some quantitative predictions that somehow mimics the physics that I'm observing in these driven systems. So I am not the one that invented that. So, but I will be telling you about something called exclusion processes. So you will see that's almost a caricature of a physical system, but you have to bear with me. You'll see that it's actually very interesting in terms of predictions. The technical thing that I want to tell you about has to do with how we can describe these macroscopic systems using the fact that they are actually macroscopic, meaning that fluctuations within these systems are usually small. And whenever we have small noise, we can do things. That's the macroscopic fluctuation theory. Then one important result of the first half will be that you'll see that driven systems, they somehow always generate long-range interactions. So in spite of the system, being short-range in its interactions, you will see that somehow long-range interactions are generated. And maybe there is the hope that in spite of having short-range interactions, you will be able, even in one dimension, to produce space transitions. Then that's what I'd like to cover to finish with today. So I don't know where I will get. Probably that's a very ambitious menu, but I will be sketchy and you will have notes if you want to read about all this. Okay, good. So let me begin with the description of the system that I want to work with, and it's deceptively simple. And so let's try with this. Oh, I should use capital letters. I was told that's macroscopic fluctuation theory. So the first thing I will be doing is I will tell you about what the simple symmetric exclusion process is. So That's very simple. I will go from the pan with the heat and the cold to something which is a caricature. So after all, in the pan problem, you can see that it's a one-dimensional problem. You see from below, there's a cold, and everything is going to be probably, not really, actually, not in the picture that I showed you, but in some regime, at least, things will be translationally invariant in the X and Y directions, but not, of course, in the Z direction. So why bothering about working in 3 dimensions? Let's work in 1 dimension, okay? So first approximation that I will do is that it's good enough to be working in 1 space dimension. Then the other thing that I will do is I will use this. It's always easier when you work on a lattice rather than working in the continuum. I certainly don't want to deal with a system of interacting particles that are mutually, experiencing Lagrange potentials. That's going to be a mess. So I will go to the discrete and I will, put some very simple interactions, hopefully retaining enough physics, but this we will not know until the end of the calculation. Okay, so here is the system that I will be considering. Just a line, a 1-dimensional lattice with lattice sites numbered from 1 to L. That's my life. That's my pan. Okay, the water in the pan, or the fluid in the pan. Then, of course, I have to talk about the fluid particles. What are they? They will be just random walkers. So a random walker can hop right and left, and I will put some, they will be doing, hope it's not me, yeah. They will be doing random walks, symmetric random walks, right and left. So that guy can hop right and left with the same probability, and between t and t plus dt, I will assume that it has a probability dt, which gives me a scale already, to hop right, for instance, and the same probability dt to hop left. Good. That's all good, but then it's just an ideal gas if there's just one particle or if the particles are transparent to each other. So now I'll put some interactions. And if I think of a Lagrange potential, I see that at short range, the particles mutually repel, and I'll keep that. Okay, that's the only thing I will keep, and I will do things actually in a very simple way. I will prohibit this particle here to jump to the right if the right-hand side, the right nearest neighbor, is already occupied. So that's somehow the simplest system that you can think of. It retains some interactions, short-range interactions. It's 1-dimensional, it's on a lattice. Not even sure that there will be interesting physics in there, okay? But I'll trust there will be. You shouldn't be fooled by the simplicity of this thing, all right? There are, I'm not going to describe them, but there are lots of mathematical mappings to quantum spin chains. It's actually an XXX chain. And its dynamical properties are related to many of the properties that are, they have like a mirror image in condensed matter. But I will be, just working within the realm of classical stochastic processes, particles hopping on the line. Okay, so this thing that I just described to you is the simple, symmetric, because they hop right and left without bias. Exclusion, because they cannot be more than one. And it's a process, because that's how I defined it. Right. So, okay, good. But that's still complicated, right? Still not so easy to do things. If I would write something about the occupation numbers, at each lattice site, the occupation number is 0 or 1, because I cannot have more than mutually exclude. So what I can do is I can perhaps see how the mean occupation number at some location I evolves in time. And if I do the math right, you will see that it evolves in a very, very simple way. It evolves in the form of a diffusion equation. There is nothing trivial about that, because it's not a diffusion equation with a unit diffusion constant. it's not trivial because the particles are mutually interacting, and in general, you don't have a diffusion constant for the collective modes that is independent of the density. Here, it turns out that due to the particle hole symmetry, that system is simple enough that the average local particle numbers, they just evolve according to a simple diffusion equation, as if the system were made of transparent particles, right? So that's already a good sign that there will be simple things here. Whether it will be too simple, I don't know yet. Okay, good. I'm not really interested in describing things at the level of the lattice. Of course, I will be using the lattice as a, you know, as a scale from which I can build the physics, but really, I'm interested in the macroscopic properties. So what I will be doing is I will be introducing some continuous, hopefully continuous field, rho, that depends on x and tau. And that thing is just the equivalent of the local particle number, in which I have scaled x as being I divided by L. And already by doing that, you see that I squeeze my whole system into 0, 1, which means I automatically look at a macroscopic system at a macroscopic scale. And because I have to adapt the time scale at which I'm working, and because this is diffusion, the natural time scale to introduce, if I want to have some hope of having some smooth dynamics for the field rho, is simply the original microscopic time in units of L squared. That's just the time that it takes for density fluctuation to be washed out by the diffusive process. Okay, so this is just rho, and to be honest, this is not very very clean what I'm doing. In principle, what I should be doing is a true coarse graining, and this is why it's not so easy mathematically speaking. I should define maybe this field as being the sum of the local particle numbers around I, in maybe up in a region of size L, and then divide by the length of the interval. Okay, that's a better definition of a smoothened density field. It's still, rho is still fluctuating. It's between 0 and 1, but it's smooth because it's coarse grained over some scale L. Here I will choose L much bigger than the lattice spacing, which is unity in my picture, but much smaller than the macroscopic scale. Okay, so that's something that I want to focus on. I want to look at this density field. Of course, because this coarse graining operation is linear in the NIs, in the occupation numbers, I can from the start write that on average, there will be a diffusion equation for my field rho. That's nothing mysterious. So the first thing that I'd like to comment on is, of course, if I forget about the average, things will not be so different because I'm working at the scale of the system, and fluctuations will be 1 over root the system size. So if the system size is infinite, it's almost deterministic dynamics. I just expect here that there will be 1 over root L fluctuations. Some noise, exactly, and as Laetitia was describing this morning. There will be noise due to the diffusion process and to the coarse graining procedure, perhaps. So at least I know things are under control. Of course, I would love to know more about this noise term here, whether it's short range, whether it has memory, whether it itself depends on density or not. These are things I'd like to know. Okay, let's wait, and I'll get there. Okay, good. So if you have questions, you should feel free to ask. Okay. Good. So, of course, what I know for sure is that even at the level of fluctuating densities, it can only be that this takes the form of a conservation equation because I'm conserving locally the particle number. So my J here, my local current, I know what it looks like. There has to be some thick diffusion term that accounts for this diffusion term here, and there will be fluctuations. How about fluctuations? Well, I know a few things about fluctuations, right? I know that if there are no particles, there will be no fluctuations. I know also that if the system is full of particles, density is 1, there will be no fluctuations. Yeah, because how can there be? And I know also that from a Poisson distribution, the variance usually of fluctuations is proportional to density. So this gives me a few hints and a few leads to postulate something for the noise. I want something that vanishes when rho is 0, that vanishes when rho is 1, that at small density, when it's a Poisson process, when I have an ideal gas, the variance behaves as rho. I know that the variance decays as 1 over L. That's giving me already a lot of food to work from. So here is what I will propose, right? Plus some white noise. And then I'll comment on that. Short range, because actually there are no, I know there's equilibrium measure here, and I will tell you more about that in a second. And it's almost correct. The only thing that I cannot guess by talking you into that is the factor 2 here, okay? But otherwise, I think it's understandable for everyone that, yeah, if there are fluctuations, they must be of that form. Good. So maybe before I dive into non-equilibrium physics, I'll tell you a little bit about what's happening in equilibrium so that we can make sure that whatever I described here is consistent with our knowledge of equilibrium. Okay, so forget about dynamics. Dynamics is time reversible here. There's obviously detailed balance. In equilibrium, I can actually predict the probability of occurrence of a microscopic state. So what is the sort of microscopic state that I'm interested in? I'm asking about the probability that I will find n particles in, say, a segment of length L, right? That's a quantity that I'm interested in. And I know that all configurations are equally likely in this problem, so I can work out by simple combinatorics. Can work it out by simple combinatorics. So first of all, I will count the number of possibilities, number of possible ways of placing exactly n particles in a segment of L sites. And if I have n particles in my system, that's just the number of ways that I can place them, small n of them, in a small L segment. And I have to divide by the total number of possibilities of configurations in my system. So that's the probability of observing n particles in a segment of a length L. Okay, good. So I told you I'm interested in what's happening for L large, but not as large as the system size. I'll also be interested in large particle numbers in my box, but smaller than the total particle number. So I'll be working in that scaling limit in which I have a finite density of particles. Let me call that rho. That's finite. And let's see what comes out if I somehow use the Stirling formula, blah, blah, to determine the form of this probability. And perhaps this is not a surprise to you. I'm not going to detail the calculations here, but I expect it to decay exponentially with the size of the interval that I'm working in. And here I have f a function, sorry, the difference of a function and f of rho is simply rho log rho. Oh, maybe I shouldn't write it like that. Sorry. L f of rho. That's my f of rho, and that's just what I expect from a bimodal distribution. Okay, you can work it out if you like using the Stirling formula, but I think everyone agrees that this is a reasonable statement. Good. So here I already know things about what's happening in equilibrium. So that tells me that the probability of observing, maybe I should call, yeah, probability of observing a full profile in equilibrium will necessarily decay as exponential minus L. And I will use L, what should I use? Yes. L being dx times L, okay, in my coarse graining, times an integral between 0 and 1 of rho of x log rho of x divided by rho 0 plus the same. Okay. So that's the probability of observing a given density profile in my system. Of course, I know on average the density profile is flat. There will be rho 0 particles. There is nothing happening here, okay? But that tells me the probability of a fluctuation. And if the fluctuation is small, maybe I can do some sort of quadratic approximation around the mean, the flat profile, and I will find Gaussian fluctuations. If rho is actually rho 0 plus some small fluctuation, then you can expand this free energy here that appears, and you will find very simple fluctuations consistent with the Langevin equation that I wrote for the density field, okay? Keep the quadratic part in f of rho 0 plus phi. So I'm not showing you why this is consistent with the Langevin equation that I somehow postulated for the density field, but it's all good. It means that whatever equation, dynamical equation, Langevin equation I postulated for the density field, it's consistent with what I know in equilibrium. So for me, I'm happy with that. I would like to tell you that it's actually a mathematical field of its own to be able to construct in a mathematically controlled fashion this continuum limit for rho. It's been done mostly by people in Rome and one in Brazil, actually, I guess in Rio. I should give you names. I'm afraid that I'm going to miss some names. But the first one that understood the importance of that limit and the fact that there will be some universal features that can be extracted from there is Herbert Spohn. Yeah. Good. So now I'm at a stage in which I have defined to you a simplified model with remnants of interactions. I have a dynamical description of that, and now I can think of, okay, well, how can I mimic the Pan experiment, the Rayleigh-Bénard experiment, using my symmetric simple exclusion process? Well, it's not really hard. If you think of it, you just take your system, site L, site 1, and what you will do is that you will inject particles with a rate alpha. Of course, if the target site is empty, or you will remove some of them with a rate, gamma. And at the other end, you will remove some of them with the rate beta and inject some of them with rate delta. These two things at the two ends, they are reservoirs of particles. I'm not driving energy here because I don't have a conservation law for energy, but I'm driving particle current because I have conservation of the number of particles. So here, things are very simple. I'm tuning the two reservoirs with rates, and they have their own chemical potentials. And if the chemical potentials of these two reservoirs are unequal, then I will generate a current through the system, right? So how do I know about the chemical potential? Not so easy, but we can make progress maybe in understanding what's happening. Of course, I can repeat what I did before. I can try and write an equation for the average local occupation number, right? And actually, there is absolutely no reason that the equation is different from before, at least for any lattice site that is in between the boundaries. Now I have to be a little more careful if I want to describe what's happening at the two ends, because this is where the driving comes into play. And at the two ends, if I will just write one just for the example. If I am injecting particles at a rate alpha, this is possible only if site one is empty, and I can only remove particles if there is a particle. So that would be, for instance, the specific equation telling me what's happening. And of course, there is a possibility of having particles hopping right or left, which I should not forget about. So this is telling me about the contact of my system with the left reservoir. That's a microscopic description of what it is to be in contact with a not a thermostat here, it's a particle reservoir. Good. So, and to be honest, everyone can probably guess that if I would go to the average profile, I would just have exactly as before, the same, except that now at one end, whatever the time, I would have some given density, let me call that rho zero. And at the other end, I would have some fixed density, say rho one, imposed by whatever right and left reservoirs I have designed. Of course, if rho one equals rho zero, I still am back onto an equilibrium system. Else, this is just an out of equilibrium system. And I'm driving a particle current through it, and it's not hard to find the expression of the current. In the stationary state, you just remove this, solve for the stationary state, and you've got, not surprisingly, a linear profile for the density. So let's talk about this linear profile. This is 0. This is rho of x. Let's call rho 0 here, rho 1 here. And yep, that's a linear density profile. Nothing so exciting. Well, let's see. Now, let me ask the very, very simple question. In equilibrium, I was able to describe fluctuations around the flat profile. They were given by just a simple Gaussian, right? Just expanding a local functional around a neat flat profile, that was not hard. So now if I ask the same question, how about fluctuations around this profile that is not straight, that is a straight line, but that isn't flat? That's a very difficult question. I can ask more. I can ask, what is the probability of observing a full profile in the stationary state? And that question is actually very difficult. It was answered only in 2000. Probability of observing a full profile. So what I'll try and describe now in the remaining few minutes on this first half is how we can at least understand that it's non-trivial to find the probability of observing a full profile, because there are some interesting physical phenomena that take place. All right, so let me maybe. Let's focus on fluctuations out of equilibrium. So I have this density, and I have fluctuations here, right? And I want to know how these fluctuations are correlated with each other. That's the simplest thing I can ask. If I ask about the whole distribution of fluctuations, this is a difficult question. So I will use the tools that I have with me. That's the simple description in terms of a Langevin equation with noise, and I'll see what I can do. Okay, so my starting point is just this. And J is the fixed part. I have this multiplicative noise that is not very nice, but still I can do things. And I have the boundary conditions. Oh, sorry. Well, I can ask exactly the same question as an equilibrium. So how about making things, looking at small fluctuations? So I will assume that my deviation of my field with respect, now it's not rho zero, right? At each location X, it's a different value of the field. That's rho stationary of X. And rho stationary of X, let me recall it, is just this linear profile. But nobody likes doing perturbation around something that is not constant, right? But that's life. So can I write an equation for this phi here? If fluctuations are small, maybe it's not so hard. I just have to linearize the dynamics, right? Oh, sorry. And there will be some diffusion term. And the thing that is maybe not so trivial is what to do here with the noise part. Okay, and to linear order, if psi is my fluctuation scale, I will just replace here the density with its steady state average value. That's the only thing I will do. So I have a linear equation that I can solve. It's a linear diffusion equation, so I can solve. I can find phi of x and tau as a function of the noise. And then I can certainly look at fluctuations. I just have to multiply the values of these phi's at 2 different times. And I will be able to express that in terms of noise correlations and a whole mess involving the stationary profile, rho s, and the Laplacian operator that is governing diffusion, et cetera, et cetera. It's not very simple, but it's somehow straightforward in terms of spirit, in terms of what we really have to do. So again, the guy that did that for the first time, let me repeat because I want this to be very clear, is Herbert Spohn in '83. Okay, so not hard. From here, I get phi as a function of xi, linear functional. So then I can compute the product, average over xi, and there I am. Yep. And I can find the correlations in the stationary state. So this is not a very, given the time that I have, I'm not going to go into the details of that calculation. It will be in the notes. But let me give you the result because the result is very, very interesting. So, and because I want to be able to compare my non-equilibrium situation with the equilibrium one, I will focus on the specific equal time correlations in the stationary state. That's the closest that I can think of to what's happening in equilibrium, to density fluctuations in equilibrium. So let me give you the expression. Oh, okay. Sorry. The expression of the fluctuations. So you crank, you do your math, you use your Green's function, et cetera, and this is what you arrive at. So let me write it in full, maybe. Yep, it's going to be nicer this way. So at equal times, in the stationary state, of course, now nothing depends on the time tau at which I'm doing the measurement. I have the following correlation function. I have one piece that is involving only short range physics. And I have one piece that is absolutely new. And the function g here, I will give it to you. It's just g of xy, and I will tell you what the okay. So after you've done the calculation, this is what you end up with. And I'd like to comment on the physics of this term first. This term is a short range term, right? If the system were in equilibrium, you would simply have rho 0 here instead of rho SS. There would be correlations on site. Of course, locally, you're correlated with yourself. So that first term is a term that says, okay, in the fluctuations, you will have a contribution that is exactly as if each individual site were independent, were in contact with an equilibrium reservoir at a given density that is space varying, that is given by rho stationary. So that's somehow the local equilibrium contribution here. As if, you know, each site were in contact with its own independent reservoir. It doesn't tell me about collective effects or anything. So that's the local equilibrium, if you wish, the local equilibrium contribution to the correlations. The second term is much, much more interesting here. So, okay, because you're all super sleepy, let me ask, does anyone recognize the function G? At least there's one who did his thesis on Coulomb system that could answer. No? So it's actually the solution to the Coulomb, it's the solution to the Poisson equation with specific boundary conditions in one dimension. So if I would look at this function in the middle of my system, not close to the boundaries 0 and 1, I would find something that is basically, x minus y with x that is given by x minus 1/2 and y that is given by this. Meaning that if I would sit in the middle of my system, what I have, what emerges for the correlations is actually the Coulomb potential between the two locations. The Coulomb potential is something, you know, in one dimension. This is exactly the potential between two charged planes. This is something that is long range. So what I'm just showing you here is a very important result, I think. It's the emergence of long range Coulomb-Lang interactions that are generated by the fact that rho 0 and rho 1 are different. So the simple fact of driving my system out of equilibrium by imposing unequal densities at both ends drives through the generates through the system long-range correlations akin to the Coulomb interactions, which are unscreened, very long range, et cetera, et cetera. So that's a huge change of physics. So let me just, you know, conclude with that, because that's long-range correlations. So I started off with only short-range interactions, and really there is nothing suspicious about, you know, particles that mutually exclude each other. And as you could see in equilibrium, it was just, you know, a very simple system, doesn't generate any long-range physics. Here, the first thing I see is that the moment I drive the system out of equilibrium, poof, I generate interactions that are super long range. By integrating these local density fluctuations, I can get the total number of particles fluctuations in my system by integrating in space. There is a contribution that comes from the local equilibrium. And integrating this function G between 0 and 1 gives, it turns out it gives 1/12. So let me just tell you about the result. So that's the true out of equilibrium contribution. So maybe I'm not able yet to speak about the distribution of the density in the stationary state, but at least I know that from the point of view of correlations, it's huge what's happening. I have the systems become stiffer, particles speak to each other from one end to the other of the system, and I am reducing fluctuations. So now this raises something, this raises a bit of a question. One theorem that holds in equilibrium statistical mechanics is that if you have short-range interactions, you cannot witness a phase transition in one space dimension. I do have short-range interactions, but I can see that they generate out of equilibrium long-range correlations. Is there a way that I can somehow trigger a phase transition down to dimension 1 just using somehow the non-equilibrium nature of the dynamics. So that's what I'd like to illustrate in the remaining time. If you have questions, don't let me just alone here while you're happily digesting. You should, help me a little bit. Okay, again. Thank you. It means it's if every location of my system were in contact with its own reservoir, imposing local density rho stationary, maybe space dependent, but independent, then that's the sort of contribution I would have. I would have a contribution coming from the local equilibrium. The lock means local equilibrium. And the rest is really the thing due to the Coulomb interactions. So don't be fooled by that, because I've been working with scales in which L is super large. I'm working with a rescaled position. In fact, there should be a 1 over L here if I were working in the proper units. Okay, so it's weak. It's weak because I'm driving the system by the boundaries. So it's unlikely that by driving the system out of equilibrium through the boundaries, I will generate something that is very powerful. But at the same time, probably around the same years, a bit later, people thought, okay, if I drive the system a bit, in a bit of a more firm manner, will I be able to generate phase transitions? So that's what I'd like to describe now. I will take exactly the same system, and you can think of it really as being the workhorse of non-equilibrium statistical mechanics. It's something very simple, almost the simplest, and already you can see that there is some non-trivial physics in there. Of course, there are people that have been working out the true Rayleigh-Benard experiment, that have been understanding the conspiration of the hydrodynamic fields and how this generates long-range correlations when you take into account all the conservation laws. But already here, you've got enough of physics, I think. So what I'd like to tell you now is about the possibility of phase transition in dimension 1, and with a question mark. So because this was a winning model, I'll take it again. I'll just, maybe I'll tweak it a little bit, that I can see that this is simple enough, it keeps enough physics, so I will do the same. I will just keep that model, and I'll see what happens if I maybe drive it a little bit more firmly out of equilibrium, and then I'll try to describe the emergent physics. So model is very simple then. Same lattice, 1D. But now I want to drive the system not through the boundaries, because I can see that because of the boundary drive, the influence on the fluctuations is 1 over the system size. So that's a bit weak, right? So what I'll do is I will drive the system within the bulk. I will imagine that each particle has a biased motion, super biased. I will think of them as being charged particles, for instance, or cars that are driven by some external fields, and therefore my particle can hop right between t and t plus dt with probability dt, but it can never hop left, as if it was pushed by some external field. Of course, now that's obvious that I'm pushing hard on my system, much harder than by the boundaries. But I need to keep some interactions, otherwise I will just be dealing with the physics of an ideal gas. So if there is a particle here, that guy doesn't have the right to hop. However, this one can hop. And of course, if I do that and the system is closed, all the particles will lump together at one end, which I don't want. So I allow them to get out with the rate beta, and I inject them with the rate alpha. Of course, you can immediately see why this is an interesting model that was proposed independently. I think the first occurrence of that model is for transport along proteins in the cell. But more recently, in the 80s, 90s, it was used to model traffic. Think of the particles as being cars entering the highway with a given rate alpha and getting out with a rate beta at whatever exit there is. And you think of that, okay, I want to describe what's happening in there. Will there be traffic jams? Well, obviously, if you If you take alpha very large, but beta very small, you will just, jam the system, and it will maybe, have difficulties in carrying through. The particles, the cars will have difficulties in carrying through. If you take beta super large, you will just, whatever is happening, you will just pump it out of the system. So that's also something that is rather easy to describe. Actually, both extreme situations are situations in which the particle current is very small. If alpha is very large, the system is super dense. Maybe there are lots of particles, lots of cars, but no one is moving forward, so the current is very small. On the other hand, if beta is large, it's fine. All the cars that are there, they can move freely, but there are very few of them. So the current also is small. So maybe you expect that there will be a combination of these alphas and betas in which, the current that you can actually push through the system is going to be large enough. Probably it's possible to guess what the maximal current is in that kind of system, but let's not dwell on that right now. Okay, so that's my system. So first thing that I'd like to ask, okay, what is the density profile? It's just a simple question, right? Same question as before. What can I tell about the average density profile? Unfortunately, the trick that I use, going to some sort of fluctuating hydrodynamics in which everything is governed by diffusion, doesn't work, because the fluctuations are not really Gaussian. They are not really of diffusive nature. They are more KPZ-like, Burgers-like, like in hydrodynamics. And that prevents me from using these scaling, this sort of scaling description. So I have to do something else. So either you know how to solve this exactly, that's good, but not super easy, or you try something that we all try at some point. You try mean field, and if mean field is good, then you're happy. So a bit of a paradox here. I will do mean field. And I told you that I was after something that has to do with phase transitions in dimension one. So it's not super clever maybe to use mean field in dimension one, because we know that we cannot trust mean field in dimension one. Probably you know that if you take an Ising model in one dimension, you're able to predict the existence of a phase transition in mean field, which is not really smart. Okay, so let me tell you why this is more difficult than previously. First thing, let me tell you about the mean field description, and then I will tell you what people have done. I will just be very descriptive to find the exact solution and confirm the mean field results, okay? So let's write, just as before, some evolution equations for the evolution of the particle number. So an I is 0 and 1, just as before, and I can write an evolution equation for the average of this Ni. So at one location, this Ni varies because particles leave, so I will have a loss term, or because particles come. Right, suppose this is I. Well, if particles at I leaves to the right, then I'm losing some Ni, and if there is one coming from the left, then I'm gaining. Of course, we know again that it should take the form of a conservation equation, even though it's discrete, just because I'm not neither creating nor destroying any particles here. So I know it has to be having that form. And the local particle current from I to I plus 1 is 1 if I have a particle at I and a void at I plus 1. So that's this thing here. So that random variable is 1 if I have a particle at I and a void at I plus 1. It is 0 otherwise. So the particle current is just the average of that guy. Okay. So already you see that this is not very nice, because unlike the equilibrium or the weakly driven out of equilibrium case of the previous example, now I need to know about two-body correlations. Unfortunately, the equation for the evolution of Ni doesn't simplify into a nice-looking diffusion equation. Yeah, that's life. So this is actually Well, if I were courageous, then I would have to write an evolution equation for the current that would probably couple to three body correlations, then et cetera, et cetera. That's just the first equation of the BBGKY hierarchy that I'm writing here. There's no way I can close it. It's a fully interacting system, and it doesn't reduce to a simple diffusion equation, period. Okay, and this is when we have to do something as physicists. We can trust our instincts and go to mean field, or we can be very bright and invent ways of solving things without doing approximation, but we have to do things, right? So what I will tell you now is about mean field. And in mean field, it's not very complicated to see what's going to happen. This current from I to I plus 1, I will, instead of saying this is the average of a two-body correlations, I will just say, well, it's the product of two one-body averages. So in the mean field approximation, I will just say something like that. Yep. That's mean field, or one version of mean field, one uncontrolled version of mean field, but that's what I will be doing because I want to get to a result. So things here are a bit simpler now because I will use the fact that I'm in one dimension. That is instrumental in making things simpler. And I will use the mean field approximation. So first of all, in the steady state, when I'm writing this, and that's not an approximation actually, and that's a feature of working in one dimension, this is 0 in the steady state. Nothing depends on time anymore. So that means that whatever gi is a constant. That's always true. And that's really a feature of working in one dimension. That's why people prefer solving one-dimensional problems than two-dimensional ones, okay? Good. So now, if I denote by rho I the average of ni, then you see that my local current is in the mean field approximation given by this. Of course, I still have, oops, not very, yep. That's not very smart. I still need to write what's happening at the boundaries. I still need to understand how the system is made in contact with the boundaries. So at I equals 1, this is the evolution for the local occupation number at site 1. And it's almost the same as before. And of course, there is the possibility of having particles that are flowing from site 1 to site 2. This is J2. So this I will call J1, right? So that guy is also alpha 1 minus rho 1. And it's also the current that is going out. Sorry. So at both ends, I have conditions of the current on the current. In the bulk of the system, I know my particles, move right and et cetera, how they transfer the particle current. So when I'm looking at this, there's a sigh of relief somehow because I know that I can solve this. Maybe not in the usual form, but if you look more carefully, this looks like almost a senior high school exercise. Almost. Probably all of you have been looking at recursions of that form at some point in high school, or maybe senior freshman year, right? A sequence that you just iterate. Of course, it's a bit of a strange sequence because I know what's happening at the boundaries, but still it's a sequence. And we know how to study these things, right? At least we know how we learn We learned how to study that. And the first thing to do is to look for fixed points, because we know that if we start close to a fixed point, then the iteration of the sequence will stay there. Okay, so it's actually a very simple sequence. So I can search for the fixed points, and I can study their stability, etc., etc. Maybe a plot will be good enough. If I'm plotting the function f as a function of x, it does something like that, right? This is, yep. And the question I'm asking is whether there are intersections with the curve x. So will depend on j, of course. Maybe there will be one, maybe there will be two, etc. That I don't know. So maybe in some cases there will be two intersections. Maybe in some other cases there won't be. Actually, there are always two intersections on condition that j is less than 1/4, and only one if j is 1/4. You cannot have j larger than 1/4 because that would j 1/4 corresponds to an organization of the system in which you have the particle, the void, the particle, the hot, and that's the best you can achieve, right? So here are my two fixed points, and what I know is that if I initiate the sequence from here, and because I can see the derivative is very small here, I will stay there. It's a stable fixed point. Good. So what does it mean that I don't get to choose where I initiate the sequence, actually? It depends on row one. And row one is J1, sorry, is this thing. So of course, I need to understand for what range of J, alpha, and beta, it's okay to initialize the sequence with rho plus. If I choose rho 1 equals rho plus, good. But if I choose rho 1 equals rho plus, this is going to fix J and perhaps the range of alpha and beta that I'm working with. Why is that? Because I have the expressions for rho plus and minus that I didn't dare to write, but maybe it's actually good to write them. Yeah, of course I don't find them, and it's not a big deal. Yep, 1/2 plus minus root 1 minus 4j. So asking for rho 1 to be equal to rho plus is going to fix j and alpha and beta. It's going to constrain the range of these parameters. So that's one thing. Of course, you could also think of starting off from the repulsive fixed point here. And then what's going to happen is that you will, if you start close enough, you will stay close to that point a long, long time, lots of iterations. And at the very end, you will deviate exponentially fast. So again, this will correspond to a range of j and alpha and beta. So let me summarize the various findings in terms of these parameters, and then we can talk about the physics. So this is the alpha and beta phase parameter space. And what I expect, what I expect is that if alpha is going to be very large, I'm going to go with a very high density system. And I already said that if beta is actually very large, I expect a low density phase. And because I have the particle hole symmetry, when I exchange alpha and beta, the hole dynamics is invariant upon changing particles into holes. I can be sure that the phase diagram will be symmetric in alpha and beta. That's the low density. So it turns out if you solve the equations, the mean field equations that I just described, and work out the range of alpha and beta and j in which all these things happen, you've got the parameter space that is split into three pieces with actual phase transitions as you get across these separating lines. So here, maybe you can guess what's happening. Here, the current is the largest. It's called the maximal current phase. So this is rather astounding because at the cost of, I would say, mathematics resembling that of first year of university, I can actually find the phase diagram of a strongly non-equilibrium system. And what I find is that I have a system that is in which the parameter space is harboring three phase transitions between the low and high density phase, high density and maximal current phase, et cetera, et cetera. So it's I think rather amazing that you have this. This is very unexpected, but of course there's the question of whether this is true. Yeah, but let me just stress the conclusion here. There are phase transitions in d equals 1 in mean field. Okay. So this is remarkable. As I said, this is something confirmed by numerical simulation. That's good, even in the 90s. Yeah. So computers existed back then. And now the real question is, what in this solution that I just posted is actually true in general or exactly? Is there anything that is, quantitatively true in this mean field description of the phase diagram? And the answer is remarkably, everything is true here at this level. Everything holds when you go to the exact solution. Everything, except when you start looking into correlations or the fine properties of the profile. Then you start seeing deviations from the mean field solution. But the phase diagram is exact. So that's, and how do we know that? Because someone found the exact solution. Actually, two people. The first one, and right after Günther Schütz, Bernard Derrida, and it's 90. I'm afraid that I'm mixing up the dates, but it's around these dates. So I'm not going to tell you how they got to the exact solution because it's complicated and it's actually specific to a family of models that I don't think this is really, useful for you in the future, right now at least. But I'd like to comment on how we can do things, and how we can understand that in this problem, some of the physics will be different from the diffusive dynamics that I described before. So, okay, so now we have this system that we know how to describe in mean field that has phase transitions, and we guess that it cannot be described by diffusing hydrodynamics. Why not? After all, why not trying? We can write equations, continuous equations, and see what comes out of that for the local density field. We can do that. So if I insisted in writing something like that, I would certainly have to write up a continuity equation because I know that locally the particles are conserved. That's one thing. The next thing I would have to do is work out what is the expression of the local particle current. Yeah, sure, the particles are driven, but there is some level of stochasticity. So there will be a bit of diffusion. Okay, diffusion tells me that I have a bit of a Fick's law. That's one thing. Next, they are driven. So I need to somehow incorporate in my description the terms that will express the fact that the particles are driven. And if there is an electric field E, then I know that the current of particles is E times the density, right? So here, I expect that there will be a current proportional to the density. I have to be a bit more cautious here because I have this particle Hole symmetry. And whatever I assert for the particles, I need it to be true also for the holes. So very likely the term that I should be adding here times E should have the particle Hole symmetry. Otherwise, it's not valid. It's pure phenomenology, pure guesses, educated guesses, but just pure guesses. And of course, there will be some noise. And what do I do with that? Well, you cannot do much actually, because this is something called this is something known from hydrodynamics, and it's called the Noisy-Burgers equation. It turns out that it maps to a host of other problems in statistical mechanics, including surface growth, as described by the KPZ equation. So something from the 80s. So Noisy-Burgers equation in 1D and KPZ equation, that's the same sort of things. And we know that unfortunately, things are difficult. We cannot solve. We know that the diffusive limit is not correct, simply because of fluctuations that correlate with each other, scale after scale. The global diffusive process doesn't go as in normal diffusion. If I would tag one of the particles, and I will look at its mean square displacement, I would not find t to the 1. That is not what I would find. I would find, I think t to the, no, I am, maybe I'm wrong. No, I need my notes because I am screwing things here. And I don't want to write things that are going to be posted for eternity on the internet that are wrong. True. Let me write it in the way that I know how to write it. Otherwise, it will be even more of a mess. Yeah, okay. Sorry. I hope this is not an insult to KPZ. Okay, so this is super diffusive, which means that whatever approximation or study of your problem that you base on the diffusive hydrodynamics is not correct, because actually the scale at which things happen in terms of the system size is not L squared, but L to the 3/2. So it's a very different scale, very different scalings. And with this, you understand that hidden in this one-dimensional physics of an out of equilibrium system with a drive that hosts several phase transitions, you also have anomalous fluctuations. And that's a very sure sign of anomalous fluctuations. So I don't know exactly what you know here. Perhaps some of you have heard about phase transitions, the Ising model, and the fact that at criticality, things are never governed by mean field unless you sit in a very high spatial dimension. So this is the first question that comes to mind is there like an upper critical dimension in which, things, this is 1D, but maybe in dimension 25, things become diffusive again? I don't know. This is a question. Is there a way to build a field theory that would lead us to be able to describe critical fluctuations or critical scaling here? That's also something interesting. And Leticia very briefly brushed upon the techniques that allow to do that earlier today. And I'm not going to go into these details. And of course, then the question is, what's happening in 2D? Do we have exact solutions, et cetera, et cetera? So this opens to the study of critical fluctuations. And as I said, in 1D, there is a connection to surface growth. The connection stops being true in dimension 2. So you have to study that on your own, blah, blah, et cetera, et cetera. So here, what I have done in this almost an hour and 20 minutes now, is I have tried to give you, so let me just briefly now summarize so that there is a clear take-home message. And I want to give you some names. So what I began with was telling you that you shouldn't be too cautious whenever you're interested in some physical phenomenon. Just begin by stripping the physical system of all its irrelevant features so that you can focus on what really matters. I started with a fluid in a pan, and I ended up with particles, zeros and one hopping on a line. Okay, and that's really important. So simplify. The second take-home message is that when there is a boundary drive, it generates long-range correlations. There is no level of generality in what I described to you. It was just one example. I could have made it more general, and if you're interested, you can look into these things because there are of course many examples, solvables or half solvables, etc., etc. And even books have been written on this. But that's the most important. If you are driving a system through its boundaries, it's going to generate long-range correlations. And if you push hard enough, you can even have phase transitions, even down to one space dimension. So that's huge, really. They are triggered by the non-equilibrium nature of the dynamics. So I have a very poor view of who is doing what in Latin America, but what I know is that in Rio, there is a lab called IMPA, in which they actually work on these lattice models, these hydrodynamic descriptions, fluctuating hydrodynamics, interacting particle systems, and so there is a big community here that is in Rio that is working on that around Landim and other people. And I think also in Buenos Aires in math. In the math department. And also you have several groups working on that in Europe, and I'm happy to tell you about these groups whenever I'm asked about that. If you so wish, just come to me during the breaks, and I'll be happy to tell you more. So that's all these people working on macroscopic fluctuation theory, the description in terms of fluctuating hydrodynamics. This is a rather lively field. The question is, what do you do with that? What kind of physical questions you ask about that? There are mathematical questions and a few physical questions. It depends on what you're interested in. Now, the idea of working on of exactly solvable models in 1D, this is a niche activity, I would say, that is found mostly, to my knowledge, in some European countries, in some cities, Edinburgh, Paris, Rome, and in several places in Germany. And for which I don't immediately see a counterpart, a local counterpart, but maybe this is just my one-sided view. With this, I think it's good that I stop here. Thank you for digesting silently, and if there are questions, I'm happy to take them.
Okay, well, we have time for a couple of questions. Okay, so now we can go to the coffee break, but first we have a group picture outside the building. So please, we can go to the picture, to the photo, okay? And then the coffee break. La conferencia es a las 8:30. Entonces, como desde las 8. Entonces, si mañana paso, que se siente mucho la semana. Estoy bien y te vas a México como 10 años. La semana pasada, la semana santa, toda la semana. ¿Qué tal la comida? ¿Qué hicieron? Playa, cenotes. Playa. A ver, ¿dónde? Sí. Pero falta todavía. Evento. Está bien desarrollado. Sí. Ah, no. Sí. Sí. Todavía no hay. Hola, Lady, ¿estás por ahí? Lady.
Hola,
Hola, ¿qué tal?
¿cómo
Gracias por
estás?
participar. En este momento estamos en el coffee break, por eso está vacío, pero ya deben llegar, ¿listo?
Ah,
Están
bueno,
afuera. Pero
bueno.
pues de tu pantalla.
¿Qué?
Entonces,
Eh,
el video, más o menos 12, 13 minutos de presentación y luego algo para preguntas. ¿Listo?
ok.
Entonces, te deja compartir.
Sí se escucha bien, es que no sé qué tal sea la señal acá, es que estoy en el C3, pero es la primera vez que estoy acá.
Escuchamos. Se
¿Sí?
escucha bien en el auditorio, está transmitiendo.
Ajá.
Solo que no hay...
Solo que, ¿qué?
Listo, ahí está. Entonces, bueno, ya está. Veo la numeración de tus diapositivas a la izquierda.
Ajá. A ver, espera. ¿Ahí se ve?
Muy bien. Sí, listo, ahí ya está. Ujú. Entonces, espéranos unos minutos y yo ya les digo que entre a todos los cafés. Y ya, pero eso va a ser en 10 minutos. ¿Sí? Pero ahí está.
Bueno,
¿Listo?
listo.
Bueno, pues, ya vuelvo. Ah, espera, entonces, tú más. Entonces, más o menos 12, 13 minutos que te tardes está bien. Cuando te falten 5, yo te hago así la cámara.
Bueno, yo creo que está como para 13, 14, por ahí. Es que,
Ya estamos en ti.
o sea,
¿Listo?
¿cuánto es el tiempo cuál es el tiempo total?
Pues en realidad son 15. Y luego
Ajá.
5. Vamos a
Ah,
ver.
ok.
Tú que causas muchas
Pero
preguntas.
te siento entrecortado. ¿Tú no me sientes entrecortada la comunicación?
No, yo te siento bien. Lo que pasa es que estoy hablando con otro micrófono.
Ah,
¿Listo?
ok, ok. Bueno,
Pero al auditorio se te escucha bien. ¿Listo?
vale. Ujú.
Vuelvo. Ya vuelvo. Chao.
Vale, chao.
Hola, ¿todo bien?
Hola. Sí.
Espera, que todavía están en el café. Pero ya, 5 minutos. Yo te los traigo a todos. ¿Listo? Ahí está la
Bueno.
cámara.
¿Qué?
De aquí te podemos ver y también vemos tu presentación bien.
Ah, bueno.
You are in the meeting.
Hola Lady, ¿nos escuchas?
Sí,
Sí.
sí, te escucho.
Okay, welcome to the afternoon session of conferences. So we have first our invited speaker, Lady Caterina Erazo, which is going to talk about anti-fragility of stochastic transport on networks with damage. So Lady, you can go.
Thank you and good afternoon. And thank you for the invitation to this workshop. Today I'm going to talk about anti-fragility. So, we usually associate damage with degradation of the functions of systems. However, there are scenarios where the damage can act as a constructive element of them. So in these cases, the systems can benefit from damage, and it is what we call anti-fragility. The immune system is an example of an antifragile one, since it can benefit from exposures to viruses or bacteria. There are also some studies that show that in road networks, if you block certain streets, the traffic flow there can improve due to this. The term antifragile was coined by Nasib Taleb in his book, and here you can find different examples of antifragile systems across different areas of knowledge. But despite the interesting features of antifragility, there are a lot of questions about it that are not that not have a satisfactory answer. For instance, we are not sure about the mechanisms behind antifragility or what kind of systems can exhibit antifragility. And another question is how to characterize it. So in this work, we present a model for antifragility using random walks on networks with damage. Well, networks are a set of nodes that represents the parts of a system, and they are connected by means of links, which represent the relationships between them. Well, here we have n, which is the number of nodes of the networks, and this quantity is the number of edges or links. And the adjacency matrix help us to represent the topology of a network. And the element aij of this adjacency matrix is 1 if the node I is connected to node j, and 0 otherwise. Here I have an example of a network with 5 nodes. And with the arrows, I am representing the direction of the connections. So here we can look that the node 1 is connected to node 2. So the element A12 is 1. And the node 1 is not connected to node 3. So this element here is 0. Well, in our model, damage represents the reduction in the weights of the edges of the network. And in that, so we need to define a matrix of weight for our networks with damage. In the case of damage in just one edge of the networks, in this case the edge AB, we have this matrix of weights. So it's quite similar to the adjacency matrix, but here we have this element that has been reduced to 1 minus beta. Beta. So this beta parameter helps us to quantify the damage in the network. It can be 0 or 1. 0 indicates that we don't have damage in the network, and 1 represents the remotion of the edge AB in the network. And with this information, we can define the transition probabilities for our random walker that moves in this network. Here I have an example of a network with damage in the edge AB. So here we have its matrix of weights. Here we can observe the effects of damage in the weights. And this is the transition matrix for the random walker that moves in this network. And we observe here the effects of damage in the transition probabilities for the cases when we move from node A to other nodes in the network, especially the transition probability to move from A to B has decreased, and the others has increased. And now we need to have a quantity that help us to quantify the effects of damage in the in these networks, especially something that helps us to measure the transport capacity of these networks with damage. So we use this functionality, and this expression is in terms of these global times that represent the average time that a random walker needs to reach any node in the network. So here we have tau 0, which represents this global time for networks without damage, and this tau beta for networks with damage in one edge. And here I represent the evolution of the functionality in terms of this parameter beta. And I choose 3 edges of these networks. And in the case of the edge that goes from B to C, we observe that this functionality decreases with damage, and which represents a degradation of the transport capacity of this network. So this edge, as we see here, is fragile. But in the other cases, when we have this link that goes from C to B or that goes from A to B, we observe an increment in this parameter. And it is what we call antifragility. So here we can see how the system benefits from this damage. And this is something that we can identify in our network. So here we have this quantity that helps us to identify the antifragile links or the fragile links in the network. So lambda, if lambda is positive, it represents antifragility. If lambda is negative, it represents fragility. And if lambda is equal to 0, it represents robustness. For this network, we have this color bar that encodes the values of lambda, and basically we can observe that these red edges are the most antifragile here. And we can do this for other networks. So here I present these graphs with 4 and 5 nodes, and we can observe here the antifragile edges in each one. And basically the main result or the main conclusion of this result is that antifragility can appear in networks with a heterogeneous topology and with these parts that are densely connected. And this result also allows us to extend this analysis to a different scale when we can analyze the antifragility at the level of communities in the networks. Here a community is a group of nodes that are strongly connected, as we see here. And in this case of affecting these communities, we are using damage that is distributed in all the edges of the communities. And for these cases, we have this measure that allow us to identify if a community is fragile or antifragile. It is basically an average of the lambda values for the edges in the community. And in the case that this quantity is positive, we say that the community is antifragile. And if this parameter is negative, we say that the community is fragile. Here we observe the evolution of this functionality for these cases. And for this example here, we observe that this functionality increases for several values of this type that here represent the damage. We observe something similar here. But in the case of this central community for this graph, we observe that this functionality decreases with damage. So it is an antifragile community, and we observe that its measure is negative, as we see. Well, Now we explore this anti-fragility in networks with heterogeneous communities with different sizes and that are not completely connected, like in the last example. And here we have this set of different networks that were, and we use this parameter, which is called modularity, to identify how defined the communities are in the network. Well, basically the main result here was that in all the networks that we analyzed, we found at least one anti-fragile community. Here I show the evolution of this functionality for some examples of these networks, and we can appreciate the anti-fragile behavior for them. And especially here we find that the networks with more defined communities have the most anti-fragile response to damage. And well, finally, we analyzed this anti-fragility in 4 real networks. We have this network that represents the social interactions between members of the karate club. Here we have something similar. Here we have a network that represents the social interactions between a group of bottlenose dolphins. And these networks that we have here represent the systems, the metro systems in Paris, and this belongs to London. We found its communities. We started to analyze the anti-fragility of these communities, and we find that in the first network and in the network associated to the Metro of Paris, we have one anti-fragile community that we have here, and here the evolution of its functionality in terms of damage. And in the others, we find that these red communities are at least robust. So, we can say that basically this anti-fragility is can be found in real systems. So it is important and interesting to study this phenomena. So now, just to finish my presentation, I want to show you some final remarks. And I want to say that in our model, we show the emergence of anti-fragility in stochastic transport. We find also that the anti-fragility emerges in networks with communities. And I think that one of the important results were the these identify parts of a network to the level of edges and to the level of communities. And finally, I would like to say that this methodology can be applied to another different dynamical systems in order to study the emergence of anti-fragility there. And here I present the paper in which this talk was, in which I based this talk. And thank you for your attention.
Thank you. Questions?
Thank you for the talk. I have actually 3 questions. I will try to make them clear, but I will ask the 3 questions at the same time. So first is, it's about the definition of your fragility. I have the feeling, but maybe it's wrong, that it's dominated, irrespective of what's happening with beta, it's dominated by the already very sluggish links, because it's defined in terms of first passages, and it seems to me that it's dominated by whatever is the slow process in your problem, irrespective of your beta. Then I have another question about the systems that you have chosen to apply your analysis to. I think I would have loved to see things applied to epidemic networks, because then we know they are somehow, scale free, and cutting or affecting one link can be having dramatic effects. So I was wondering if you had this in your mind for future works. And the final question is more theoretical or mathematical. Of course, in 1D or on the beta lattice, you can probably work things out exactly, and perhaps from there you can also understand the effect of loops in some way. So that's these are 3 questions, and I'd be happy to have your reactions on that.
Well, sorry, but you can repeat the first question. I didn't understand well.
Yeah, the first question is that your definition of fragility is based on first passage times, right? It's the average first passage time, meaning that you sum over all possible vertices and you average that over. This summation will be dominated by the vertices that it takes the longest to reach, right? So I was wondering whether it was a sensitive enough quantity to define fragility, and if you had other definitions in mind that would give maybe less weight to these extreme events.
Well, yes, as you say, basically this functionality here is in terms of this global time that depends on the main first passage time for the random walker in the network. And but in this case, we are using this parameter to reduce the weight of the links in the network. And well, but actually, this I think that this definition, that the definition that we are using here, help us to explore the global transport here in the network. And well, maybe I am not sure about what do you mean with the sorry, can you repeat the last part of the question, because I didn't understand that part. Sorry.
It's fine.
Another question?
So, well, in the with respect to the applying this methodology to the to epidemics or something like that, yes, that could be a good work for. It could be a good application of this methodology. In fact, we have another works where we study the effects in systems that synchronize too.
Sí, ¿no? Ah, sí. Ah, se nos cortó la. Bueno, había entonces another question back there.
Hi, first of all, thank you for your presentation, Dr. Eraso. I see that the anti-fragility that you report emerges specifically in networks with high modularity. Had you explored where there is a modularity threshold or limit below which the system transitions from anti-fragile to fragile in a discrete manner analogous to a phase transition? If so, does this threshold depend of the degree distribution in the network? Thank you.
Okay. Well, we don't have a study about the threshold in which this anti-fragility emerged in these networks with communities, and I think that it could be something that we can do later. But yes, in fact, as we see here, basically in networks with these structures that are really connected, we obtain the more, or we get the most antifragile links here. But maybe we can study which is the point, or which is the threshold in which these start to disappear.
Thank you so much.
Okay, thank you. Well, thank you, Catherine. So,
Thank you.
well, we move into the next talk, which is by Juan Felipe Alayon. So, I'll give the stage.
Hello, everyone. Okay. Okay. Oh. Uh, okay. Hello, everyone. I'm really happy to be here. It's the first time that I made something like that, like this kind of conference. I'm a little bit nervous, but it's okay. I will present my first paper here that is called From Motive to Levy Flights, Modeling Urban Mobility in Bogota Public Transport System. So the content of my presentation is really short, like my motivation, the methods and the results. I really want to talk about my motivation because I think that is really important. First of all, when I studied physics, I always wanted to do something that could be useful for the people. So I noticed that here in Bogota cities, there are a lot of problems related with mobility. So I decided to do something with our public transportation system that is really important. And some people could call it that is a mess. And the other motivation is something more about the curiosity that I have to know how the people move here in Bogota cities. So with that in mind, I have two main two main different objectives. The first one is create the best OD matrix, origin destination matrix, and the other one is to solve the equation that I did. Okay. Okay, first of all, I really want to give the context for the people who are not here from Colombia, especially from Bogota cities. When I talk about the public transportation system, I'm talking about four modes that are integrated. The main two are a BRT system with some specific ways in the city. The others are buses, mixed buses, and aerial trainway that is really important here in Colombia because we have a lot of mountains. Unfortunately, in Bogota City, we only have one that is not that good. But something interesting of the system is that we have the possibility to make something that is called the transfers. That transfers means that you, with the same amount of money, with the one payment, you can use one BRT system and two buses, for example. There are other forms to use it, but that is the main. Every day, a Transmilenio system take 4 million people per day. And every day, every person when use the system, the enterprise take the data of that registration. For 2 years with the Professor Alejandro, we took the data from July 2023 to June 2025. We also analyzed more than 2,300 million records. There is a lot of data. We divided that in 4 semesters. It was more about organization, but we also wanted to analyze the of how many use the people the system. For example, in the table we can see that, for example, the 2 uses are like the most common thing. Okay, but what happened with the other uses? With the transfer system, we have the possibility to use the system many times. Okay. First we make like some statistical patterns. The first one was about the time. There is not too many things to say here. The most important thing, I think, that is in work days, the people have like very specific patterns, no matter if it's in, for example, December or January. There are the most common vacational time. The average go a little bit down, but it's not really important. Another thing to talk about is about Saturdays. Saturdays are like the mix into work days and a rest day. This is not common if we saw studies like this in other cities like New York or Chicago. Okay, we also wanted to make like a special pattern. So we divided the city in like specific squares to make a better organization when we create the OD matrix. So as you can see, you can see how many people go to any specific zone that we create in the morning and in the afternoon. It's really interesting because if someone hears now the Transmilenio map of the BRT system, we can see it in the data. That was really interesting and really cool too. But now we're going to talk about motif. Something that is motif is a graph or a network that repeats a lot of times. For example, come here to the National University, I have to talk to 2 buses, and then I will take other 2. So I have to make 4 registrations. And there are a lot of people that make exactly the same trip as me, and that repeats many times. So we wanted to analyze that in different ways. And with that, we have like these 11 results. That is the most frequent motif. This is like 96% of the data. And with that, we noticed that it's important to take into account different ways in which the people move. It's not just like in the traditional way that people go to their home and then return. No, it's a little bit more complex. And with that logic, something important to say is that we, like Transmilenio, as most of the transport system in the world, only have entries not exist like recordings. So for that reason, to create a audio matrix or the motif that I showed it was necessary to follow a specific logic. Logic was like, for example, I have two entries, so I take the first one as a origin and the second one as destination, and I follow this logic if they are more. So we create a OD matrix. This is the total OD matrix, but we also created like the OD matrix for 2 trips, 3 trips, 4, and 5 and 6. So we added, and we have here the result. The other one, the yellow one, is the OD matrix, but for distance that will be very important in the future. So we wanted to analyze that our logic have some sense to take into account more than just 2 trips. So we use Jensen-Shannon criterion to know if it has a sense or not. So we actually noticed that the more data or the more trips we take into account, the more information we get. We also make the same comparison between the semesters to see how is the behavior of the city, because the city have been changing a lot for the construction of the metro or another 2 lines of Transmilenio, or the change that the system has. Okay, we create the OD matrix, so we are going to solve the second questions without. So we're going to talk about Levy flights. The first image in the top is about Brownian motion. I think that the most people here know how Brownian motion works. So a Levy flight is basically the generalization part. It's really similar with, for example, imagine that you are a random walk and you have the possibility to make like any kind of jump with some probabilities. The Levy flag make that you have the possibility to make big jumps, like go for really long distance, as you can see in the image. Another important thing to say is that in many cases you have the possibility to go to your local part and then make a jump. And then we have something that is called probability transition, a transition probability, sorry. We have here 2 definitions. The main one is based on the OD matrix, and the other one was is a model that was proposed by the Professor Alejandro and the Professor Jose Luis Mateos in the past. And it works really well. The second one works with the distance, and the first one with the OD matrix specifically. So we really wanted to analyze if our city could move as a Levy flag. So we make like the logarithm between the transition probability and the logarithm of the distance. We have that distribution that could be considered as a Levy flight with a gamma of 0.92. We really wanted to know if that have sense or not. So we propose like a way using the Kullback-Leibler divergency to know if the results that we get are good or not. So we propose that MKLS, that is a measure of the Kullback-Leibler divergency. So the minimum part will be the perfect or the correct value of the gamma. Finally, we also wanted to know when this gamma starts to appear. So in the first image, we calculate the gamma between delta t, there is delta time. That means, for example, that delta time means that we got the data for the first month, and then the data for the first 2 months, for the first 3 months, and then like that. We notice that after the 6th month, we have like established an equilibrium, sorry, and then after the 16, I guess, 16, 17, we can see that it starts to growing up. That means that something happened in the city, and as I was telling you, the city have been changed a lot those years. And finally, we wanted to make like something that makes that our data and our results are true. So we make a Monte Carlo simulation that are the last 2 images between different times, and we we have like well, with the Monte Carlo, we noticed that actually the simulation, it's really similar to the real data that we took. Finally, the conclusions are really simple and short, I guess, but are really important. The first one is that we have the possibility to make the best OD matrix. That is a really powerful tool, especially if the people of mobility want to do something with that. And the second one is that people here in Bogota move as a levy flight. That means that the people have to make long trips to get what they need. For example, work, study, or simply for enjoy the time. And finally, this is like a first step for doing something that could be very useful for the people. We can make like other methods, for example, with artificial intelligence or something like that, and that's fine. And finally, if you are interested or you want to know more about the topic, you have the possibility to take scan the code and or talk with me or the Professor Alejandro if you are interested.
Are there any questions? Yeah.
Thank you. So in your data, you showed that was like a histogram of the times people traveled on Saturdays.
Okay.
There was I'm always going to be asking about oscillations, I guess. There was a kind of oscillation that seemed to match like the hours of the day. Do you think this is from, yeah, on the Saturdays, there's like a little, on the Saturday especially, it looks like a very clear oscillation of a period of like an hour.
Yeah.
Is that from the way the data is collected, or is it like a feature of people, I don't know, meeting people on the hour or something, do you think?
That is really curious because as you can see, for example, in the work days, you can see there is like a perfect curve line, but there are a lot of peaks here. That means that not all the time and all the people go out in the same time. For example, I don't know, a Saturday or Friday, for example, a Monday you just finish your job and go to your home. But maybe a Saturday you start to, I don't know, go take some beer with your college or whatever, and you go out to your home a little bit later. So that depends in many things. But it's really, really, really interesting that it's appear. That could be something very interesting to analyze a little bit more deep.
Thank you.
Have time for one more question? No? Okay.
Thank you for your presentation. I want to make a question about the predictability and future investor outlaying this concept. So given that Bogota's mobility patterns follow level flags and remain stable according to the JSD, Jensen-Shannon divergence, how robust do you think is this model for simulating the impact of the upcoming metro line? Could JSD be used as a validation to see if the metro actually closes the gap that you mentioned before between the peripheral and central travel distribution, or if it simply reinforces the existing level-like patterns?
Okay, this is a really good question. And in my point of view, I can see that the metro lines and the way in which the metro line is planned, for example, because the metro line has like in the top and the Transmilenio will be in the down. That makes that the station between the metro lines doesn't have to be like very close as most part of the city. So that means that maybe here we have to make like these long travels, and the long travel that the old metro will make will be in less time that now the people took. So I think that the pattern of make the long trip will still existing because it's more about the organization of the city, because the people move long in a long way because they need it. It's not just for they want it. Maybe the metro could make the experience of traveling in Bogota will be better.
Well, thank you very much. So our next speaker is Jefferson Rubiano.
Buenas tardes, ¿me escuchan bien? Ok, that's good. Bueno, hoy voy a presentar en español, entonces voy a presentar el estudio termodinámico del fenómeno de formación de opinión en un modelo que se llama el modelo DNA-W. ¿Listo? Estoy trabajando en mi doctorado con el profesor Carlos Kimbay, pues mi nombre es Jefferson Rubiano. Bueno, listo. Creo que ya pasó. Listo, ahora sí. Creo que ya. Entonces, pues la agenda de la charla, voy a dar un preámbulo inicial, un poco de contexto social y sociofísico al proceso de formación de opinión, algo de la perspectiva termoestadística que se está estudiando. Entraré pues a explicar el modelo de influencia limitada y convergencia de NW, unas posibles aplicaciones y algunas preguntas. Voy a dejar esta pregunta inicial como reflexión. Pues, a ver ustedes al final qué opinan. Si la opinión se crea o se transforma. ¿Listo? Para que lo tengan ahí. La opinión se crea o se transforma. Listo. ¿Por qué es importante estudiar el fenómeno de formación de opinión? Pues vemos que esto tiene que ver con políticas públicas, con democracia, participación ciudadana, con tendencias de mercado, con temas de economía cultural y pues cualquier otro tipo de tendencia que se dé en este proceso de formación de opinión. Desde las ciencias humanas se ha estudiado el fenómeno de formación de opinión a través de algunos factores, ustedes los ven a la derecha en esa columna, a través de la persuasión, percepción, convicción, cognición, influencia, distanciamiento y otros. Son importantes estos que están resaltados en color rojo porque ahora los vamos a tocar de nuevo. Desde el punto de vista sociofísico, en física se ha estudiado el fenómeno de formación de opinión a través de estos modelos, entonces colisión de partículas, temas de agentes, procesos de magnetización, temas de polarización de opinión, temas de transición de fase como procesos de solidificación o percolación, buscando consensos de opinión, en procesos difusivos a través de modelos aleatorios de partículas, temas de difusión de opinión. Ya un poco más específico para el tema de modelos basados en agentes, que es lo que voy a presentar a continuación, pues hay modelos, como ustedes ven, de simulaciones multiagentes, ecuaciones síndicas de Boltzmann, ecuaciones cinéticas tipo Fokker-Plan, y pues vemos que en algunos casos las ecuaciones son lineales, en otros son no lineales estocásticas, en otros son modelos integro-diferenciales, ecuaciones diferenciales parciales, y en particular pues tienen enfoques microscópicos o enfoques macro. El que se va a presentar ahora es un enfoque micro. Bien, entonces aquí empezamos un poco a entender, este es un modelo de intercambio cinético, entonces en principio imaginamos como un gas de partículas donde dos agentes intercambian opinión a través de un, un choque binario o un intercambio de partículas. Eh, para lo que vamos a trabajar, lo que vamos a estudiar es la opinión de un agente I, se nota con O sub I en el tiempo T, en T más 1. ¿Listo? Entonces hay un intercambio de opinión entre un par de agentes y al final pues tienen en el tiempo T una opinión e intercambian opinión en un tiempo T más 1 y cada uno pues queda con una opinión diferente. ¿Cómo se relaciona esto con un sistema de partículas, con un sistema de gas ideal? Pues que en el gas ideal Es un sistema de partículas, en el sistema social es un sistema de N agentes, en el gas es un tema de energía interna, ¿de acuerdo? En el sistema social es un tema de opinión, donde la opinión total, pues en este modelo se conserva, la temperatura se relaciona con, como ustedes ven ahí en la diapositiva, pues la energía interna dividido el número de agentes multiplicado por la constante, y allá pues será el número total de opinión dividido el número de agentes en el sistema. Como en un gas de partículas, pues la energía antes y después del choque se conserva. En este caso, para un sistema cerrado, pues en este modelo también se conserva la opinión de los agentes antes y después del intercambio. Esto es muy básico del modelo, pero es muy importante porque ha sido bastante estudiado y bastante citado el modelo. Entonces ahí de manera muy rápida, en las dos columnas, donde aparece gas ideal y en el otro donde aparece sistema social de opinión, pues aparecen las relaciones y digamos las analogías. En un caso una partícula, en otro caso agente, colisión elástica, intercambio, en un tema, digamos, conservación de energía, ya puede ser conservación de opinión. Variables macro del estado, pues la energía interna, el número de partículas y la temperatura, ya es una opinión social. Todo lo que tenga S es social, entonces opinión social, número de partículas, temperatura social. Y pues, digamos, otras variables macro que se estudian como la entropía, digamos acá el potencial químico, relacionados con la primera, segunda y tercera ley de la termodinámica, que tienen, digamos, su analogía en un sistema social. Bien, aquí lo que es importante es cómo se define la temperatura, que a partir de la temperatura es que podemos definir las otras variables macro, y en este caso se definió como, digamos, el primer momento absoluto central de la distribución de opiniones de agentes. Y usualmente en los modelos que nosotros estudiamos en termodinámica, pues estudiamos las fluctuaciones a través de la varianza. Entonces esto es importante y ahora más tarde pues tal vez lo mencione. Un poco de este modelo, entonces se llama el modelo de NW por los autores, Defoe, Nu, Frederick Ambler and Ray Gerald Weibush, y hay un poco de el seguimiento que se hizo al artículo. Pues es que el artículo ha sido muy citado y también trabajado en otros contextos, por ejemplo, Fortunato lo cita mucho y Castellano en su Physical Review de de estadística para modelación social. ¿Listo? Bueno, entonces entrando ahora sí en materia, nosotros vamos a definir un número total de agentes. A cada agente le asignamos una opinión, ¿de acuerdo? A través de una distribución uniforme, una opinión entre 0 y 1. Y pues un agente I tiene una opinión antes del intercambio, al igual que un agente J. ¿Qué pasa, por ejemplo, en el recuadro está? Cuando intercambian opinión, pues intercambian opinión a través de la diferencia que ellos dos tengan en su opinión. Y lo multiplicamos acá por un factor que se llama mu. Mu en este modelo se llama la convergencia, ¿de acuerdo? Pues lo que uno observa en el modelo es que eso se aproxima usualmente al valor promedio de la opinión de los dos agentes. ¿Qué es lo interesante? Que existe una ventana donde los agentes pueden o no compartir su opinión, que es aquí este D que ustedes ven aquí. Entonces este modelo lo que hace es asigna a cada agente una manera de intercambiar su opinión para un momento T más 1 y digamos lo limita a que existe una ventana. Es decir, que si un agente tiene no sé, una opinión 0 y otro tiene una opinión 1 en el tiempo t igual 0, y si la ventana es, por ejemplo, de 0,5, pues nunca podrán intercambiar su opinión, ¿sí? En caso de que los dos tengan opiniones muy diferentes. Y bueno, este parámetro se llama el parámetro de convergencia y SD se llama influencia limitada o confianza limitada en los modelos. Entonces aquí un ejemplo rápido. ¿Qué pasa en esta regla de intercambio si mu es igual a 0? Pues entonces ustedes observan si iniciamos con una opinión 0,2 o una opinión 0,8 en el agente Y y en el agente J, pues si aplicamos esa regla de intercambio, vemos que el agente Y va a tener una opinión 0,26 y el agente J una opinión 0,74, o sea, muy cercanas a la opinión que ellos traen inicialmente. O sea que ese parámetro mu en este modelo lo que hace es, de alguna manera, permitir el intercambio, pero se da de manera muy suave. ¿Qué pasa si, por ejemplo, hacemos el parámetro de convergencia cercano a 0,5? Pues que las opiniones muy rápidamente se van a acercar a 0,5. ¿Y qué pasa si hacemos entonces el parámetro muy grande? Pues que las opiniones, además de que se cruzan, o sea, no llega, digamos, si uno tenía una opinión inicial, como en el ejemplo, 0,2 y el otro 0,8, si dejamos un muy largo, muy grande, pues van a cruzarse las opiniones. O sea, este puede ser más grande que el que traía inicialmente y este puede ser mucho más pequeño que el que traía. Pero pues en el tiempo eso tiende a estabilizarse y no habría ningún problema. Entonces, como conclusión, para ese parámetro mu, pues hay un cambio lento en la opinión cuando mu es muy pequeño, hay un cambio rápido y se equilibra muy fácil a un consenso de opinión, y cuando mu es muy grande, pues hay un cambio drástico de la opinión, pero al final también llega a un consenso. ¿Listo? ¿Qué pasa entonces en el modelo de manera particular? Pues que este D controla el número de consensos que se puedan tener en un sistema de n agentes. Entonces a la izquierda ustedes ven es la función de entropía, aquí es la distribución de opinión calculando también la opinión promedio, y aquí es la distribución de los agentes en el tiempo. Entonces uno observa que en un tiempo igual a 0, pues todos los agentes tienen una opinión aleatoria entre 0 y 1, viene a través de una distribución uniforme, pero ¿qué pasa con el tiempo? A través de esa regla de intercambio, pues que todos los agentes llegan a un consenso 0,5. En este caso, cuando cambiamos el D, lo que vemos es que el D modula o controla de alguna manera los consensos de opinión cuando el D es menor. En este caso, D es igual a 0,5, en este otro caso, D es igual a 0,25, y pues vemos que se forma una polarización. Nosotros en estos modelos también podemos de alguna manera medir entonces la entropía, entonces podemos definir, por ejemplo, si acá hay un consenso cuando este sistema llega a su estado estacionario, entonces pues en este caso vemos que la entropía mínima para el de 0,5 es 0, y en este caso la entropía pues cambia de valor 0 a un valor mucho más pequeño, en este caso 0,69, que se calcula con la entropía de Shannon de forma usual. ¿Listo? Bueno, esta es una parte muy importante, pues definimos entonces la temperatura de esta manera como la probabilidad, y siempre lo comparamos con la opinión promedio del sistema. Para una distribución uniforme, pues digamos en esta regla de intercambio que es conservativa, la opinión promedio siempre va a ser un medio, ¿de acuerdo? Y lo medimos a través de un número de bines. O sea que ponemos la distribución, definimos un número de bines, a cada bin le calculamos la probabilidad de que la gente tenga una opinión dentro del bin, y lo que hacemos es calcular la opinión del bin menos la opinión promedio, ¿de acuerdo? De todo el sistema. Al final, ¿qué encontramos? Pues una temperatura T igual, bueno, T, una temperatura TS en un tiempo cero, y podemos definir adecuadamente la temperatura. Esto nos ayuda de alguna manera a entender cómo funciona el sistema y cómo es su termoestadística. Entonces, aquí para mostrar un ejemplo, en la gráfica de la izquierda, pues se tienen a través del modelo diferentes Ds, un D0125, un D025, un D05, que es el verde, pues ya sabemos que esta es la temperatura, y entonces en un sistema que ha llegado a un solo consenso, pues la temperatura es igual a 0. La entropía también en algún punto se hace 0, y ese tiempo lo llamamos el tiempo crítico, o el tiempo donde el sistema va a su estado estacionario, y pues por supuesto que si el D cambia, la temperatura final del sistema también cambia en función de esos consensos. Entonces, por ejemplo, acá vemos que para D025 la temperatura final es más baja que para T0125. Eso nos habla de la agitación del sistema. El sistema puede estar más o menos agitado. Y entonces tenemos la temperatura, la entropía, y aquí a la derecha tenemos el potencial químico, que es bastante interesante interpretar esta parte del potencial químico, porque aquí vemos también cómo cambian en función del tiempo. Y para este modelo en particular, el potencial químico lo interpretamos como la dificultad de un agente de cambiar de estado. Entonces, pues tenemos las tres gráficas y vemos que es más difícil que un agente cambie de estado. No, mentiras, es más fácil que un agente cambie de estado porque su temperatura, su potencial químico es menor. Y claro, pues porque tiene la posibilidad de, en la gráfica, de tener diferentes estados posibles donde puede saltar el agente o no. Mientras que si digamos, hay un solo consenso, pues va a ser más difícil que pueda saltar a otros estados porque ya en sí mismo está en ese estado. Conclusión, el potencial químico es una forma de medir qué pasa si un agente quiere cambiar de un estado de polarización, de un estado de consenso a otro, o quiere saltar en su estado de opinión. Bueno, aquí algunas cosas que se han hecho en simulación, que es como la entropía en función de los tamaños del sistema. Aquí el tamaño del sistema es importante, por lo que uno hace diferentes arreglos experimentales, diferentes simulaciones, hace la estadística, y pues vemos que para sistemas más grandes, pues en efecto el sistema tarda más en llegar a su estado estacionario, y también depende del D, ¿no? Entonces cuando el D es más pequeño, hay menos intercambios, entonces al sistema le tarda también mucho más en llegar a su estado estacionario. Pero la entropía nos permite ver cómo de alguna manera medir el tiempo crítico en ese estado estacionario. Y aquí lo que vemos es, perdón, aquí lo que vemos en esta última gráfica es cómo varía el tiempo en función del parámetro de convergencia. Entonces, lo que les decía inicialmente, cuando el parámetro es muy pequeño, pues las opiniones cambian muy poco en el intercambio, entonces demora bastante el sistema en llegar a su estado estacionario, al igual que cuando el parámetro de convergencia es muy alto. Cuando el parámetro de convergencia es cercano a 0,5, pues las opiniones rápidamente convergen a un punto o a un valor como consenso dado. En este caso, pues 0,5. Entonces lo que hicimos ahí fue estudiar cómo ese parámetro de convergencia dependía en el tiempo de las simulaciones. Y pues algunas perspectivas de aplicación de esto, de hecho ya hicimos con el profe alguna, tiene que ver con que pues de alguna manera si podemos hacer un análogo en temas organizacionales, podemos ver temas de decisiones colectivas. Si aplicamos esto a temas de procesos electorales, pues entendemos un poco mejor cómo es ese cambio. Y lo más importante es que a través de este modelo describe cómo es la dinámica micro, pero eso cómo hace que existan propiedades emergentes en el sistema de manera macro. ¿Listo? Eso es todo lo que tenía para presentar. ¿Alguna pregunta? Bueno, sí. ¿Qué pensaron de la pregunta? ¿Se transforma? ¿Por qué crees? Sí, sí, bien. ¿Alguna otra pregunta? Bueno, por allá atrás.
Muchas gracias por la charla. Una pregunta, ¿qué tan válido a nivel experimental es que la opinión se conserve?
¿Qué tan válido es preguntar que la opinión se conserve?
Sí, o por ejemplo, empíricamente, ¿sabes si esas suposiciones del inicio se llegan a mantener hasta cierto punto en la vida, digamos, entre comillas, real?
Digamos, bueno, algo importante mencionar. Digamos, en este modelo, vamos a poner las reglas de intercambio para entenderlo un poco. Tal vez no lo mencioné, pero si uno hace la suma antes y después de, en esta regla de intercambio específica para este modelo, tú ves que la opinión se conserva, ¿sí? Mira, si sumamos aquí, estos términos que son cruzados se cancelan en la suma y pues la opinión de antes será igual a la opinión después. En estos sistemas y en este modelo uno podría decir que sí se conserva como una variable macro del sistema, pero lo que sabemos es que en un sistema real el sistema primero no es cerrado, segundo pueden haber ruidos externos que hagan que la opinión se disipe de otra manera y al final pues haga que esto no se conserve. De hecho en la propuesta de tesis eso es lo que sucede. Estamos estudiando un modelo donde no hay conservación de opinión. Bueno, vale, gracias. ¿Listo? Gracias.
Gracias. Our next speaker is Gustavo Espinosa.
Hi, thanks for the organizer, but for this opportunity, this is my second talk in English. Sorry for my Spanglish. So for this talk, I want to show the exploration mechanism intrinsic to semantic networks and the nonsense appraisal of lexical repetition occurrences. This is some results that I, with my co-advisor Joaquín Goñi and my advisor Fernando Naranjo. In the master degree, we can to submit these results in a paper, and this is that we show today. So the fifth definition is the semantic memory, and this is our system that this type of memory store vocabulary in less word is the memory that we can store the meaning of the word without import the time in I acquire this information or the place in that I stay or the conversations. This is not important because the semantic memory only stores the relations and the meanings of the words. So this relation is our focus in the studio because the retrieval vocabulary is a retrieval information that their system have studied by the psychologists, but only qualitatively. So we propose a mathematical framework to try to model this retrieval. So we need to define an experiment and a model. Then the experiment is a semantic fluency test. It's a task or a functional task in the memory with apply this person to one category, or we try to any person give me information for a specific subcategory or specific category, in this case animals, we get this type of list that is a semantic fluency test. So we can to observe the two elements that is the, for example, exist a cluster with two words or more words can be related with a semantic information, but exist the case of the two words don't have a specific semantic relation, but exist a change in the subcategory of my principal category in the test. This change or switching and this clustering or process between the clusters it is related with the lesions in the frontal and temporal lobes. This is spectacular because the store exists in a space in the brain, but the mechanism have a physical regions that defined by the frontal and temporal lobes. So yeah, sorry. So the true mechanism is the switching, that is a change in the subcategory, and the clustering, we define to the searching within a particular cluster of the network. And the network we use for this work is the conceptual network that is the principal result of the connection between words in the fluency test, and this is a constructions using the idea that any word between a cluster can be reach another word in the same cluster. This is interesting because when used, the idea of the right conceptual network appear small word behaviors in the new network. Okay, so the last definition is the short-term memory. That is a example for a change a number specific of items that I can manipulate for the develop on the semantic fluency test. And similar to the clustering and switching mechanism, the short-term memory is affected by the temporal lobe and the and the frontal traumas, because the number of elements in the change and this manipulation can be reached in the best performance. So when you want to study this retrieval information, we propose the switching random walk using a matrix of switching and a matrix of clustering and a switching parameter that I can modulate for a specific weight in the switching matrix. So the clustering matrix is a switch random walk with only depend the degree of the H node, and the most important part is the switching matrix, because the bias that I defined in four models, equiprobable, positive gradient, negative gradient, and the frequency bias, and this is correspond to the switching mechanism and the bias to the quotidianity of any person. When we, how we can form models need to express the best model for the retrieval information and use the mean passage time and the entropy rate. The passage time defines the performance of a switching random walk, and the entropy rate is our efficiency. So in the mean passage time, we obtain the measure of number of steps that need the switching random walk to reach all nodes in the networks, and the entropy rate is the measure of efficiency, and indicates how the entropy change in each step in the random walk. When apply these conditions or these measures with the three specific case, equiprobable bias, positive gradient, and negative gradient, we observe in the case of MFPT that the decrease his values indicate a best performance in the switching walker, but when the switching level increase, the performance decrease. Why? Because exists a relation with the specific network structure. We observe this in the form of the increasing MFPT when switching level increase using an enriched conceptual network. So if a specific node have a more number of H, it's more difficult for the switching select the best option for minimizing this number of steps. And in the case of entropy rate, we observe that is more efficiency in the case of negative and equiprobable bias. In the other hand, in the enriched conceptual network, is more efficiency the equiprobable bias than the negative gradient, because the selection here is poorly by the higher number in the connections in specific networks. This is a relation with MFPT and entropy rate when the switching level varies in a range of 0 to 1. So here we try to reveal any characteristic of these models, but this not such importance mark that the relation in the case specific of the enriched in the case of the conceptual network. And in the case of the enriched conceptual network, this increment here is specific of the structure of the network. It don't depend more that the mechanism. But the interesting results appear when we using the repetitions for implement the working memory or the short-term memory. So in the case of the frequency bias, exists an increment of the number of repetition in the words when the switching level appear in a in a lower values of the Q. So this separation don't depend of my system. Depend if the depend only the characteristic in the frequency that the one word appear in a whole bulk of semantic fluency test. So when you use the short-term memory, appear this black zone that is beautiful because this is that the psychologists hope that observing in any moment, but qualitatively this not appear. But in the old mathematical system, we can see this curve. And this zone is the zone of for any health person without any trauma in a frontal or temporal lobe. And in this region, when when the switching level is lower, exists any relation with the short-term memory with specific traumas by affect the frontal lobe that the epilepsy or Huntington or maybe the schizophrenia in not all types of schizophrenia because exists a gamma of this this problem. So when you when the short-term memory in the equiprobable bias is a null hypothesis, but any person have a bias due to the quotidianity. So it's more specific or it's more real this bias that based on frequency that the whatever all model that I can construct. When observe the difference between frequency bias and the switching random walk with key probable bias, observe that similitudes in the low switching levels, but in the high switching level, the difference appear more clearly because the number of repetitions in here is more in the frequency bias than the equiprobable bias. So this is important because when the frequency is higher for a one word, imply that there exists any relation of the meaning of this word in the life on the quotidianity for the person that develop the semantic fluency test. For finish, the conclusions. The comparison between MFPT and H values, we observe that the behavior and the positive bias and the equiprobable case is inversely proportional. Yeah, the performance on the fluency test is associated with the how rich the lexical vocabulary, and our results suggest that the optimal range for word retrieval, characterized by the low number of repetitions, lies where subcategories shift are not frequent. And any consideration is this not the only model, and exists other representation for a memory storage. And in this other representation, this application of switching around the world maybe don't exist or don't we could apply. So the psychologists using variables that I will not consider how the number of clusters, the switching, the number of switching the clusters, or the size of my observation window in the fluency test. So this is a new results for psychologists, and this is a study can apply to the prevent different types of lesions in lobes. So, pues, thank you for stay here.
Thank you. Questions?
Yes, thank you very much. What do you mention that people with some injury in the frontal or temporal lobes have a different performance? No, in your model, how do you make the difference between a healthy one and one with an issue?
Okay. In our model, in a range between 0.25 and 0.50 is the optimal zone for a healed person. Over this range exists any injury in specifically because I only change the switching level, the injury is only the frontal lobe. Okay. So the temporal lobe don't apply over this range. Under this range, this only have effect of injury in the temporal lobe because the temporal is the responsibility for the searching in a clusters.
Okay. So the temporal level is more responsible for searching inside the same cluster, and the frontal lobe is more responsible for switching between.
Is totally responsible for the switching. If the frontal lobe don't respond, the switching don't appear in a person.
Okay, thank you.
Other question? How do you calculate the mean first passage time in this case?
Okay.
Do you have an analytical expression or?
Yeah. We use this expression. This expression is a mean first passage time. This is a mean of the mean first passage time, because we need to know what is the number of totally different units.
And how do you calculate each turn? DT.
Okay, DT is here.
Oh.
DEJ.
How do you calculate the?
Okay.
The other part.
We construct this fundamental matrix because the identity and the matrix of switching random walk in the study in the specific unit, and the switching random walk in the steady state.
That is using that method that removes one node and calculate the new matrix, and then you.
Yeah, this is a comparison when I init the fluency test in horse, for example, is different when I begin the semantic fluency test in a dog. Okay. So this try to occupy all the possibilities of the beginning the fluency test.
Thank you. Other questions? No? Okay, well, thank you. Well, with this we end this session for today, and we'll meet tomorrow at 8:30 here for the next course. So have a good evening.